Now we come on to the last major unit on applications, web search or information retrieval or text mining. These are three related areas. And we start actually off this particular unit. Well, the first lesson of this unit has a short discussion of data mining in general, not actually specifically for web search, but just to put everything in context and shows which things we're discussing, how they fit in the general taxonomy of approaches to data mining. Then we state the problem of web search, what the web is, and what its structure is, which parts are linked to which other parts, and there's the nice pretty shapes you can get there, and the power laws you have for the number of URLs in a page. We look at web search in general, starting with its history. It's now, of course, incredibly sophisticated, but it started off relatively simply, and you can even relate it to libraries and things like that. We have from a computer science point of view, web search starting off as information retrieval. And there are various key features of information retrieval, so-called the simplest Boolean query, yes, no answer to a set of structured queries. We have fuzzy versions of that. We have vector space models. We have probabilistic models. And here we have a little diversion to do something which I used to do when I was a child, namely to discuss the different views of statistics. Is a frequency view or the Bayesian view, which is a probability view, that actually a probability is not just a frequency, it's a measure of your belief that something is true. Then we look at the actual analytics for web search, and then going into detail, we show how to prepare a document, what the inverted index looks like, how we construct that index, how we process the query, and then we come on to the key brilliant idea which created Google, PageRank, which was because when we do web search, we don't just want to get possible answers, we have to rank them. And there's a set of concepts like hubs, authorities, and PageRank, which allow you to identify particularly good things to return to the user, and why Bing and Google and others return such wonderful results, which often seem to pick out of the tens of millions of possible responses, ones in the first page, which are so near to what you want. Then we discuss how to crawl the web. There's some interesting issues which is sort of web advertising. And then there are other ways of doing the search other than just returning documents, which are maybe better illustrated by things like Google News, where Google News actually collects clusters, many links together, which have a similar topic of interest attached to them. So there's a lot of work, actually in computer science and in industry, on so-called topic models and clustering documents together and using that to give a different type of response. And that ends those two units on web search and text mining. Then we come across, then in the next set of units corresponds to various technologies. These will differ according to the track. So this talk is for the Python track, and we start off with K-means done in Python. And we give the actual algorithm, and we actually look at the code and things like that. And we also, we know about random variables. We can actually generate artificial clusters randomly with random properties, and we cluster those. We generate them and then cluster them, and show quite amusingly how you find these false minima and things like that, and how you get pretty amusing results from time to time. Typically, you get the right answer, but actually more interesting is the wrong answer, at least for this class. It's not so interesting if you're doing if you care about the clusters for some operational issue, but for the class, the wrong answers are the most interesting. Then we have a discussion of MapReduce, which I say is a pretty mediocre discussion, and I strongly recommend you take the real class on MapReduce. And We have an introduction which uses a presentation done by Judy Chu and a student Celia on Sam, who uses blends fruit and uses the MapReduce technology to blend fruit. And that illustrates the key ideas of MapReduce. And then we look at some more advanced topics in that field. But to say this is just a brief discussion to add a little value to this particular general class. Then we have a little set of lessons on k-means and MapReduce. Here we just point out that we've modified the k-means code in the SciPy distribution so that it actually is appropriate for MapReduce, and then we run it actually and show that it gives the same answer, although we don't actually run it under MapReduce, but we do run maps followed by reduce things. So we do maps and we do reduce. We just don't run them controlled by Hadoop or some fancy MapReduce technology. But it illustrates the key idea of how you break things up into maps and you follow the maps by a reduce operation. Then we go to PageRank, and under PageRank we discuss two things, actually calculating the PageRank from a matrix, and we do simple examples of 6x6 and 8x8 matrices. And then we do the then we find out the PageRank of a real page by just extracting it from the web using a Python call to the web. So that's the end of the technologies for this particular course, the ones we cover. And then we have three final values of X. The first value of X is health informatics. We start off by broadly discussing where big data is important in health. We go through three reports: the McKinsey report on the big data revolution in US healthcare, finding out how big data is going to change everything. We have a little aside from Microsoft, a couple of slides on how they think big data is used in health. Then we have an EU report, which is not that dissimilar in flavor from the McKinsey report, but it's trying to suggest that by using all this information and making all this information available more broadly, you can really change the ground rules of health. You can make health not just health is not just focused on the wealthier people, but everybody can have good health by just making information available. Then we have a rather short discussion of clouds and health, which is pretty unsatisfactory. There is no very good discussion, as far as I can see at the moment, on clouds and health. Even though clouds are being used in health, it's currently pretty secret. And I don't know of any very good, very easy to probe places to study that. Finally, we have an area where there is plenty of information actually on using clouds. That's the core academic research in genomics and proteomics and how you visualize those things by mapping them to three dimensions. So that area is pretty solid, and that can use clouds. But using clouds to process electronic medical records or health records, that's obviously has lots of security issues, and it's very important because it will be more efficient, and in principle you can share information and make make results from one patient help other patients stay alive and things like that, but that's not so easy to find out about. Next unit is on sensors, and the sensors we illustrated by the Internet of Things, where we already pointed out that 24 to 50 billion sensors will be deployed, and by 2020, there are many. When you go to the web, you can find out lots of different answers. I found two credible answers. One was 24 and one was 50, but I'm not saying it matters so much between those numbers. They're both pretty big. Clouds are clearly wonderful architecture for processing sensors because sensors are small, and clouds love processing lots of small things. We give some examples from earth science, which sort of includes environmental and polar science. Those, a lot of that work is done by sensors, whether tiny sensors or large satellites. and we give some examples there. A very important area, interesting area for sensors, ubiquitous cities or smart homes, where we believe, or at least the world, some people in the world believes that the world will get covered by sensors. Those sensors will report all their information to the cloud. The cloud will process it and summarize it, compare it and control it and change many aspects of our life. Korea has a particular emphasis on this area with the concept of ubiquitous Korea, and they have some advantages because they have such good cell phone coverage. They have more bandwidth per people than anybody else in the world. And the final example, which is slower to do in the US because it requires working with established infrastructure, namely the electrical utility infrastructure, the so-called smart grid, where again, deploying sensors throughout the grid can help control power usage, identify faults more quickly, and so on. So the smart grid is correctly believed to be very important. And again, the cloud will process all this data. Clouds are very appropriate for lots and lots of things being gathered together. Finally, we get to a discussion of the last unit of the class, which is radar informatics. Pretty interesting area. Radar gets lots of data, requires a lot of processing, typically image processing and signal processing. The particular case we will cover here is glaciology, where we will start off with this motivation, which is clearly motivated for polar science by some rapid, slightly alarming changes of the ice sheets and the glaciers at the North and South Pole and actually on mountains. Then we'll give a broad discussion of remote sensing. We will give the background of that global climate change and why we need to integrate polar science with ocean predictions and atmosphere predictions and environmental predictions, and put them all together to give global climate change predictions. If the North and South poles melted, you would be pretty unhappy if you lived near the ocean today. We give a broad discussion of ice sheet science, a discussion of the radar and its basic technology. It then describes what we're doing at Indiana University, and which is largely in collaboration with the so-called Science and Technology Center, CRESIS, led by brilliant people at Kansas University, and then we'll discuss how we're doing it with some early results. So that's the end of this course, the last unit, and I thank everybody who's made it to this point. Let's hope that we have appropriate technology for rewarding you. Thank you very much. This is Jeffrey Fox signing off the course on Big Data Applications and Technologies and or X Informatics. Thank you very much again. Goodbye.